Hello, today we're going to look further into the thing called spacetime. We introduced spacetime in my video Spacetime and the Twins Paradox. You'll recall that spacetime is a four-dimensional creature, the normal three dimensions of space plus time. But that because three dimensions plus time is very difficult to depict or to understand or to conceptualize, to make it easy we stuck with one dimension of time and one dimension of space, which we call the x-axis. So people are free to move along the x-axis but not in the y or the z direction, just to keep things simple. And you'll recall that we said that there were two things that you couldn't do in this space-time. The first thing is you couldn't move backwards in time. This suggests that time is going upwards. This arrow suggests that you're going backwards in time, and you're not allowed to go backwards in time because there's no known mechanism for doing so. The second thing I said was that when one draws a time-space chart, we usually organise it such that the speed of light is given by the 45-degree line. And I said that you couldn't therefore travel at any speed greater than the speed of light. Anything in this area here is forbidden because that's greater than the speed of light. If you stand still, then you don't travel in the x direction at all, you simply go up the time direction. If you move, then you can, for example, go like that. That means you've travelled this distance in space and that time, but you can't go faster than the speed of light. And space-time charts are not particularly difficult. Let's, for example, take a very simple idea. Here am I wake up in the morning and I go downstairs. I haven't moved from my house. I have my breakfast. I then travel to work. Better not go too fast, otherwise I'd be exceeding the speed of light. I then work at an office. I don't change my X location, but time continues to go by. And then eventually I go back home again at the end of the day and go to bed. And that's my space-time travel. I have woken up, travelled to work, stayed at work, travelled home from work, gone to bed. That's a simple space-time diagram. Now we can draw the diagram in a slightly more complex way, and that is to say that those are the time and space coordinates, and we'll also draw in the speed of light coordinates. And what we're really saying here is that you can travel to the left or to the right on the x-axis. And of course you have to travel forwards in time. But this area here represents the past. And this area here represents the future. And this point here is now. So I am at this location in time and space now. And what we're saying is that for me, the future is this shaded area. This point here, I can never get to. It's a bit like saying I can't get to New York in 5 minutes' time. I can get to New York, but not in 5 minutes. I can get to this location in space, here okay, but I can't get there that quickly because then I'd have to travel faster than the speed of light. And similarly, my past has been constrained by this area. If I am here now, I could never, in some time in the past, have been there. Because if I had been there, I could never get here because that would require me to go faster than the speed of light. Now comes the problem that we're going to look at today. Suppose I move through space-time. I go from here to here. Let's call that travelling from point O to point P. Just to be clear, that's time and that's space. So I have moved a distance, we shall call that delta x. That means the change in distance that I have travelled from O to this point here. And I have also travelled through time delta t. So I have travelled delta x and delta t in order to get from O to P. I have travelled through space-time. The problem, of course, is, as we saw in the videos on special relativity, is that an observer who is speeding away at velocity v will look at me travelling and will come to a different assessment as to what the distances I've travelled and the time. He will say that I travelled delta x prime in a time delta t prime. And delta t prime will not equal delta t, and delta x prime will not equal delta x. And the question is there anything that these two observers agree on? Well, we did actually cover this in my videos on special relativity, but I'm just going to deal with it again here so it becomes clear. We know that if I measure a certain length x and a certain time t, so we'll call that delta x and delta t, that some other observer travelling at speed v will measure delta x prime and delta t prime. That's what we just noticed. But in the videos on special relativity, we found that there is a relationship between these measurements. Delta x prime is equal to delta x minus v, which is the speed of the other observer, times delta t, divided by the square root of 1 minus v squared over c squared. And delta t prime is equal to delta t minus v, that's the speed of the other observer, divided by c squared, the speed of light, delta x, divided by 1 minus v squared over c squared. Those are the two terms that relate the length and the time measured by one person compared with the length and time measured by another person who is travelling at speed v, relative to the first person. So let's just be clear to avoid the risk of boring you, but make sure that you understand before we move on. Here is a space-time curve, and I, as the first observer, observe that a ball rolls from here to here. And I measure, according to my frame of reference, that it's travelled a distance delta x in a time delta t. But there is an observer in a spaceship going past at speed v, and they observe that that distance there is actually delta x prime, and that that time is delta t prime. And the relationship between delta x, delta t and delta x prime and delta t prime is given by these two formulae. Now, I want to consider if there's something special, and of course there is, otherwise I wouldn't be considering, in the following. C delta t prime squared, all squared, minus delta x prime squared. I want to look at that as a term and see if there's anything clever about it. Well, we've already identified what delta x and delta x prime and delta t prime are, so we can substitute these values, or this value here for delta x prime, and this value here, or this term here for delta t prime. And if we do that, if we substitute in this equation here, we shall get that this is c squared times delta t prime squared, which is delta t minus u over c squared, v over c squared, delta x squared. And I'm going to put in a term gamma squared. Gamma is 1 over the square root of 1 minus v squared over c squared. It just saves me writing it out so many times. This is this. Now I've got to do minus delta x prime squared, which is delta x minus v delta t squared times gamma squared. So this equals this. Well, now we have to multiply it all out. This is where it gets a bit laborious, but hang on in there. First of all, we can take the gammas outside to start with. Gamma squared comes outside and multiplies absolutely everything, and that will be c squared times delta t squared plus v squared over c to the fourth. I keep mixing up u's and v's. It should be v times delta x squared minus 2 delta t v over c squared delta x. That's just multiplying out that term. Now we have to take away this term here, so let's multiply that out. Delta x squared plus v squared delta t squared minus 2 delta x v delta t. So now all we've done is laboriously multiplied through. Now what we can do is to multiply this term through by c squared, because there's the c squared. We're just going to multiply everything through. So this now just becomes the gamma squared still on the outside, c squared delta t squared plus v squared over c squared delta x squared, because the c squared cancels there, minus 2 delta t v delta x minus this term here, which doesn't change, delta x squared plus v squared delta t squared minus 2 delta x v delta t. Phew! And then the bracket goes at the end, which I forgot there. Now you'll notice that here we've got minus 2 delta t v delta x minus 2 delta x v delta t. Those two terms cancel. Thank goodness for that. And now what have we got? We've got gamma squared into, gather up all the terms for delta t squared, that's delta t squared into c squared, and then here minus v squared, plus, now gather up all the terms which refer to delta x squared, so that's delta x squared into v squared over c squared minus 1. We're almost there, hang in there. Take c squared outside here, so we've got gamma squared into c squared delta t squared into 1 minus v squared over c squared. All we've done here is take c squared outside, that becomes 1, that becomes v squared over c squared, and swap these two terms round so that we now say minus delta x squared 1 minus v squared over c squared. Well, we're almost there. Do I need to do the final step? Yes, I think I better, just in case there's any problem. That's gamma squared into c squared delta t squared minus delta x squared times 1 minus v squared over c squared. But since gamma equals 1 over the square root of 1 minus v squared over c squared, gamma squared cancels this term here, and you are left with c squared delta t squared minus delta x squared. Lest you be wondering what on earth that means, let me just remind you of how we started. We started with the term all the way back up there, c delta t prime squared minus delta x prime squared, and what we've just shown is that that equals c delta t squared minus delta x squared. In other words, both observers, however they may differ in their measurements of delta t or delta x, will always agree that c squared times delta t or delta t prime squared minus delta x or delta x prime squared is a constant, and that we call s squared. So what we've just shown is that s squared is a constant for all observers, and it equals c t all squared minus x squared. In other words, it doesn't matter what speed any observer may be doing, they may all measure different values of x and different values of t, but the one thing that every single observer must agree on is that s squared equals c times whatever measure of t they have had, all squared, minus whatever measure of x they have, all squared. And what does that look like on a space-time chart? Well, here's the space-time chart. Here's the speed of light at the 45-degree angle. And what this formula looks like when plotted on this chart is it looks like something like this. It's what's known as a hyperbola. And what it means is that any point on this hyperbola satisfies this equation. Different points will have different values of x and different values of t. But when you substitute them in this formula, you find that ct squared minus x squared always comes to a constant s squared. And that's a hyperbolic function, and it's also sometimes called Minkowski space. Let's also just remember that if you travel through space-time, here's time, here's space, and you travel from point O to point P, you've travelled through space-time, you've actually travelled a distance delta x in a time delta t. And that means that your velocity v is simply the distance divided by the time. So I measure that velocity as delta x by delta t. Of course, another observer will measure different values for delta x and delta t, and therefore will get a different value for velocity. Let's imagine that I'm travelling in a car at a relatively sedate 10 miles an hour. And I am sitting in the car. And my frame of reference says that I don't move. I don't move. The car is moving, but I do not. So I am entitled to say that I am stationary. Now we're going to imagine another observer who is standing by the roadside watching me go by. We have just established that both of us will agree on a value of s squared, which is ct all squared minus x squared. But we've also just established that x is essentially velocity times time. And so we can say that s squared is ct squared minus vt all squared. Now let's consider things from my point of view sitting in the car. Remember, I am stationary in the car, so in my frame of reference I am not moving. As far as I am concerned, x is 0. And so I say s squared is ct squared. There is no x component because I'm not moving. The person by the roadside, however, measures the fact that I am moving. He measures a velocity v prime and a time t prime. So he says s squared equals ct prime squared, that is the time that he measures, minus x prime, which will simply be v t prime squared. That is the velocity he measures as my car goes by times the time which he measures. So I am measuring time t, he is measuring velocity v in time t prime. But these two values are the same because s squared is constant. Everybody measures the same s squared. So now we can say that ct squared equals ct prime squared minus vt prime squared. So just multiplying that out, c squared t squared equals c squared t prime squared minus v squared t prime squared. Divide through by c squared, we get t squared equals t prime squared minus v squared over c squared t prime squared. Or t squared equals t prime squared into 1 minus v squared over c squared. And taking the square root, we get that t equals t prime into the square root of 1 minus v squared over c squared. and you'll remember that that's the famous Lorentz transform term that's come up again. And finally, I want to look at our speed through space-time. I don't mean our speed through space, which could be a variety of things. I want to know how fast we move through space-time. Well, here is a space-time chart, time against distance. If I stand absolutely still, I will simply move through time. And we have said that that is time t. But in order to make it the same set of dimensions as the space dimension, we have to multiply by the constant c so that we get the same terms. In other words, x will be measured in meters. It's no use having t in seconds because there are two different quantities. You can't compare apples with pears. But the process of multiplying c by t is to multiply seconds by meters per second. The seconds cancel and the term ct is measured in meters. And now these two terms can be compared. So ct can now be compared with x because they're both measured in meters. So it may sound odd to measure time in meters, but that is essentially what we're doing. Now here, what do we say? We say that this person has travelled through space-time entirely in the time dimension. How far has he gone? He has gone ct meters. How long did he take to do it? T seconds. What was his speed? Distance divided by time is c. He has travelled through space-time at the speed of light. You'll notice that I didn't say he was travelling through space at the speed of light, which of course he couldn't do. He is travelling through that combination of space and time called space-time at the speed of light. But we've just shown that there is a universal quantity that everyone measures, s squared. It equals ct all squared minus x squared. Now in the case of this person here, there is no x dimension. He didn't move, he's just travelled through time. So then s squared equals ct all squared. And that means that s equals ct. T, of course, is the time that was measured on his watch as he travelled through this time here. But look, s divided by c equals t. S is a universal constant. We've already shown that. C is the speed of light. That's a universal constant. So s divided by c is t. And t has a special name. It is called the proper time. It is the time which everyone will agree on. And the proper time is the time that it takes for someone who is actually holding a clock whilst doing the travelling. And that time will always be the longest time. Anybody else observing what's going on will observe a shorter time. But everyone will be able to calculate the proper time as being s, which everyone can calculate, divided by c, which is a universal constant. And what this also means is that everyone travels through space-time at the speed of light. Not through space, but through space-time. The only question is, how do you apportion your progress through space-time? You have a choice. You can not move at all, and you can have all your speed of light travelling through time, in which case you will go the greatest amount of time. In a sense, he hasn't wasted any of his space-time speed on travelling any distance. He's used it all up in travelling through time. Compare that with somebody else who travels through distance and time. They will use up some of their space-time speed in travelling through distance and some travelling through time. So they won't go through quite as much time. And that's why you get time dilation. If that's proving a little bit difficult, consider this. Suppose you were to set out from, say, London, and you wanted to go 100 miles. Well, you could go 100 miles due north. And then you will have got as far north as you possibly can, but you won't have travelled east or west at all. Of course, you could, however, have travelled 100 miles in this direction, in which case you'd have got 100 miles east, but no miles north at all. Or you could have gone a bit of each, in which case you would get not quite 100 miles north and not quite 100 miles east. You have to make that choice. And that's what we do when we travel through space-time. Everyone travels through space-time at the speed of light. If we stand still, then we give all of our speed to time, and we travel through time at the fastest rate, which means we age. If, on the other hand, we travel through space as well as time, then we don't travel through quite as much time, and therefore we don't age as much. That is the essence of time dilation.